Next up, we have Jeff Pouilette from Florida DOT. He's going to talk to us about post-tension segmental bridge inspection and the resolution of maintenance issues. You know, I'm not going to read Jeff's bio. He's been around forever, and he's been a great partner in this group, several different places. And he is going to be stepping off the Florida DOT stage here at the end of this year. And we are certainly going to miss him, but I know he won't be a stranger. So let's give it a round for Jeff.
This presentation is broken down into 3 parts. I'm going to give a basic description of segmental bridge technology because I know some people here know what a segmental bridge is, but I want to focus in a little bit so we can, understand better what we're dealing with here. The second part of the presentation is going to be the Roosevelt Bridge case study, which kind of launched the last part, which is inspection and evaluation of PT issues and other segmental bridges and the resolution of those issues in Florida. So there are basically 2 types of segmental bridges. There's span by span, which I'm going to touch on in a minute, and there's balanced cantilever construction, which we're going to be focusing in on today. And it is exactly what it sounds like. You hang a segment on one side of the pier, and you go on the other side, and you kind of keep the load balanced over there until you get to the closure pores. And then you close the closure pore, you pour the concrete, and you post-tension across the bottom of it. Why this has been a popular erection technique is because it's self-supporting. The PT at the top is about 2.5 times what you need in the final condition. It has some advantages in terms of cost over the span by span, which you'll see why. And when I get to that, just a brief touch on it. So here is a typical balanced cantilever segment. They're cast in a casting yard. They're cast against the previously cast segment. The previously cast segment is rotated to adjust for horizontal geometry, vertical geometry, profile, deflection, anticipated deflection, shrinkage, creep, whatever else goes into that, and that's pretty much it. And then they're basically, it's moved up and they cast the next one. And what you see over here is that for a balanced cantilever segmental bridge, they have internal tendons. They're internal to the concrete, and that's part of the issue we're going to be talking about here. Also, you notice over here, you see the top temporary PT bars. That's called a blister. And on the bottom, they're showing a bottom temporary PT bars embedded in the deck slab. It could be either deck slab. Typically, blisters are used, and the only other thing of interest, of course, here is the anchorages, and that's a big interest. I'm not going to dwell on this slide. It just shows that the way it's post-tensioned, it looks a lot like you'd have for reinforcing for, if you were doing any other traditional, even smaller reinforced concrete bridge. It's the same thing. You got positive moment tendons, you got negative moment tendons. The positive moment tendons are actually called continuity tendons in this technology. This is a segment being placed using a launching gantry. This is very popular in Florida because a lot of it's done over water. You bring it out on a barge, you hoist it up, you put in your temporary PT, double face epoxy, you squeeze it, so basically theoretically you don't get any leakage, and it's not for the faint of heart. Believe me, I've been out there doing these operations, I've been on the stressing platform, and it has your attention, really. Big time. Segmental span-by-span construction is similar, except it's used on a truss, and I think that's probably why it's a little less popular, because the costs are maybe a little bit higher. But sometimes there are good places to use these too, and but you have to have 2 spans erected so you can do the negative post-tensioning across the top over there, and we have quite a few of these in Florida. The big difference on the older bridges, well, first of all, they all have external tendons. They're inside the box, and you can see them down here in the bottom over there, those pipe-looking things. Those are the tendons. And you can see up in the corner, up at the top, and the bottom, you have the blisters. Those blisters are there during erection so you can squeeze the double-face epoxy so you don't get leakage. In the end, they look pretty much the same. They have a little less post-tensioning in them, and remarkably, we've had less problems with these types of bridges, and we're going to talk about that a little bit more later. So anyway, Roosevelt Bridge was built in, when we looked at this bridge, it was 23 years old. It's US 1 and State Road 5 in Stuart, Florida. It carries crosses over the St. Lucie River, over the Dixie Highway, and over the Florida East Coast Railroad. The bridge is basically, it's twin bridges, it's 3 lanes each. It was in service 23 years before it started to develop problems. I was out there during the initial construction at the time, and I had some questions, which I guess it was kind of prophetic, but we'll get into that too. It's a post-tension segmental balanced cantilever bridge, and they're both about a mile long. On June 16, 2020, FDOT was informed that concrete had fallen off span 1 of the southbound Roosevelt Bridge. Inspectors observed, and this was called in by the public, so they sent the inspectors out. They've discovered a ruptured tendon and a large crack in span 1 southbound, and the span stability was a concern. I got a picture later on of this. Immediate actions taken. Southbound bridge and Dixie Highway beneath span 1 southbound, northbound and southbound bridges were closed. So that Dixie Highway had a bridge going across, so you took out 4 lanes of traffic in either direction, one fell swoop, and the only thing they had access on the southern side of the island, so this was a big deal. Global detours were implemented. The northbound bridge was striped for 4 lanes, 2 lanes in each direction. It was reopened on June 27, 2020, after being load rated, load tested, and posted for 5 tons. I had a lot of conversations with John Corvin. He was the engineer on this, and he was kind of nervous about doing this load rating. And he said, what are you looking for? And I said, I think we could live with 5 tons just to get the traffic on the thing. And we had a lot of discussion about the load rating, how it should be done. And in the end, that's what we did. Shoring was installed for span 1, and Dixie Highway was reconfigured and reopened on July 3rd, 2020. So this is what we saw out in the field. On the left over there, what you see is a corroded tendon. It's basically, it's neck down, you know, so it's yielded. There's loss of section, there's lots of rust. This tendon has failed, you know what I mean? And on the right is what you see is that crack. Now between that crack, if, on one direction heading off to the right, there was the end bend. So if this thing went, even though it was a continuous bridge, that span was going to fall down. And that's why the shoring was put in over there, to make sure that didn't happen. Soundings were performed to determine the locations of delamination and crack locations they were map cracked. We didn't know exactly how serious that was going to be. So they were mapping everything. Non-destructive testing was used. We're going to talk about that a little bit more. Concrete excavations were performed to determine the extent of deterioration. Observed corroded tendons on northbound and southbound bridges, and delaminated concrete was map cracked, was located. Concrete and grout samples were taken and tested for chlorides and sulfates. Usually we don't have a problem with sulfates unless we have thixotropic grout. We've had some problems in the past, but it was just one particular manufacturer, and we don't use that anymore. It's been pulled off the market, as a matter of fact. And our issue here was chlorides, and there was a big study to try to figure out what was really going on. Well, we had cracked concrete on the deck, and we were very close to the ocean, so salt was collecting on the deck, washing through the cracks, and that was the real problem over here. Findings at most excavations, concrete deterioration did not extend to the PT. Various levels of corrosion were identified, with most being minor, which thank goodness for that. In span 1 southbound, extensive PT corrosion was observed, with several tendons completely failed. Deck slabs had extensive minor cracking and water leakage. And here is some of the NDT that was used. Initially, this was GPR, and they thought they could find some anomalies, but they had a problem with connectivity because they had to have an aerial, and it was in the box, and this is moving so fast, they didn't have an aerial system put together, but what it was used for effectively was locating tendons. So on the right over here, what they're doing is they're basically plotting out where the tendons are, and they're determining exactly where you're going to have to excavate. An excavation of a tendon takes about 4 hours. It's like a root canal. It has to be done very carefully, because as soon as you nick the tendon, it's really you can't trust it. So so you want to do this extremely carefully and find out what's going on, and but it's a slow process. This is another NDT we used. It was in-house. It was air launch GPR, and the air launch, because it's on the front of the FDOT van, you can see an FDOT van. It's run by the materials office. And on the right over there, you see the plot. And green is good, red is bad, yellow is not so good, and the light pink is a little worse than the yellow. And we also used thermal thermography, but we had to contract that out. We found out very similar results, although it didn't match up 100%. So we started getting into this. We started looking at what was happening with the deck, and we found out that the red wasn't as bad as we thought, because it was really anomalies. It hadn't really gotten down to the post-tensioning and the steel to any great degree. So there wasn't a lot of damage caused to the post-tensioning system on the top post-tensioning. It was the bottom post-tensioning, the continuity tendons, that were the issue. Provisional tendons were added to both bridges, spans 9 spans northbound and 8 spans in the southbound. This is because we had some section loss, and we wanted to basically make sure that they weren't compromising capacity. Plus, the bridge has got ongoing corrosion. It's got cancer. You know, I mean, we're going to have to watch this bridge forever. I'm going to talk a little bit more about that in a minute, too. What happened was that we put in some additional provisional tendons. We used the existing blisters, and we just strengthened it a little bit, just to give us some, a little bit of buffer over here. In the span 1 southbound, the internal tendons were cut. New external PT tendons were installed with plastic ducts and flexible fill. I'm going to show that in a minute. Closure pour concrete and corroded tendons were removed, and concrete was restored. And they had to do it because the tendons in the span southbound, they had a water leak going on forever, had compromised the deck slab concrete, and we didn't want the rusting to go and destroy the bottom slab. So even though there was no post-tensioning, active post-tensioning in there, we had to get them out and restore the concrete. In order to stop water leakage in the decks, segment joints were sealed. An epoxy overlay was placed on the decks, approaches, and sidewalks, and I'm going to have a nice picture of that in a few minutes. More things are coming. Repairs to the bottom slab excavations at the closure pours for both bridges, where the concrete delamination did not extend to the tendons, concrete was restored. That was good stuff. Where corrosion was insignificant, PT was monitored, and cover was restored. After they tried to passivate this as best they could, what they did was they wire brushed it, and they used vector corrosion paint on it, and then they restored it, the concrete. So they wanted to make sure that it was passivated. And this is the inside of the box in span 1. You can see the ducts over there, the plastic ducts, which contain the tendons, and also the flexible filler, which is really basically wax. Just by doing this repair, because it was tendon for tendon replacement, it is not as strong a bridge as it was before. And the reason for that is you're close to the neutral axis, and these ducts in these wax tendons cannot develop bond, so there is a reduction in capacity. But it has like a rating factor, I think about 1.3, if I recall. So this over here is what we did at the top of the slab. And if you look over here, they have the epoxy injection they did at the between the segments and on the other wide crack they could find. They also used Kevlar over the top of the joints. Elsewhere, they used a methacrylate substance. It wasn't methacrylate, and then they put on 2 layers of epoxy overlay for it. We don't do this very often in Florida, by the way. But they had a segmental bridge they did this on years ago that didn't have any conditions, anything like this, but had leakage. It's been out there 15 years, and it's still not leaking. So this is where we decided to go, because we wanted to protect the PT in the top slab, and we definitely had to stop the leakage for the PT and the tendons in the bottom slab. And the bridge that's the final repair, and that's what it looks like. The district secretary insisted on it being Class 5, wanted to give the public a lot of confidence, and the bridge looks like it's new, really. Reopening the bridge. On November 5th, 2020, the southbound bridge was reopened to unrestricted traffic. On November 24th, 2020, the northbound and southbound bridges were opened to 3 lanes each. Conclusion and status. Roosevelt Bridge has been restored and is open to legal truckloads. Now, I made the decision that even though I had some reserve capacity because it had a rating factor of 1.3, I didn't want to see heavy loads on this bridge. So I have the control to restrict all overweight loads, and nobody challenged me on it. We had Old Dixie Highway underneath that could carry truckloads, and the other side of the island could carry truckloads. So it's a minor inconvenience to the trucking industry, but we want to protect this bridge because we don't know exactly what's happening with it long term. So we ended up decided to install a monitoring system, and this is the first monitoring system, the health monitoring system we've done in Florida, except we did a demonstration project years ago on a steel bridge that we were trying to find out more. Actually, we're legislature mandated that we do it. But it consists of acoustic emissions, which can listen for sound. It listens for strand breakage, and you can home in approximately where it is, but we're also using continuous strain monitoring to see how the bridge behaves over time. It's like anything else. This is like a human that's going through remission with, with cancer. So we want to keep track of this thing, and hopefully we can get to it before it continues. I don't think anybody believes we're going to get more than a 50-year service life on this bridge. We're going to try to keep it going as long as we can. What happened with Roosevelt Bridge opened our eyes, and senior management started asking, what's happening with the rest of our bridges? So we decided to look at the rest of our bridges, our segmental bridges, and prioritize the bridges inventory for further inspections. Task 1 was going to be the same type of thing we did before, special inspections, soundings, and visual inspections. Task 2 was going to be further inspections, investigations, excavations, material testing, and non-destructive testing, which I wish we would have used more of, and analysis, repairs, and monitoring if necessary. So if you look at this over here, this is how we went about prioritizing our bridges. We had 92 segmental bridges in the state, 56 miles of roadway, and we had 66 bridges, 23 miles of roadway that were identified for further inspection. Why? Because they had internal metal ducts. We don't use internal metal ducts anymore, and we stopped doing that a number of years ago. But internal metal ducts are not good for one reason. When I was out there on Roosevelt Bridge, and I was there, and I saw what they were doing, they were using duct tape to put the internal metal ducts together. It was a standard of the time. And the thought was that, well, the grout's going to fill everything. Well, yeah, it's not pressure tested, so you don't necessarily get the grout filling everything, and plus it's got corrugation, so you get trapped air and water. The other thing at that time was they used neat grout, which is either a cement or a sand cement grout, and that can subside, and it has subsided at high locations, and that can cause problems trapping air and water. So, and we also had poor quality closure pour. So if you take a look at this, we had a district secretary who was very avant-garde and wanted to see a lot of, nice, cool-looking bridges in his district. District 4 had the lion's share. The numbers speak for themselves. What did we do? We did pretty much the same thing we did on Roosevelt Bridge. We started soundings with a hammer, were performed on the interior and exterior of the box girders, listening for delaminations. Emphasis was given to soundings at closure pours to locate delaminations. Locations of concrete spalling were identified. Significant cracking was mapped, and special attention being paid near tendons. Of course, we saw conditions, that extended into the segments. We would follow up on that. This is a real challenge, particularly in South Florida. There's a lot of traffic in South Florida, and scheduling over the interstate is an issue. It has to be done at night. You have to use the public information office. They have to notify the public, and then you get out there. There's traffic control that has to be shifted around, and it's done with lights and everything else. And it takes a long time to do this, and you can't close everything at once. So this took a long time to do. And of course, scheduling inspections over the railroads. We had 4 spans. It took almost as long to schedule that as the inspections on the other bridges. The railroad it's a busy rail line down there, and it was tough. Status and findings. 100% of the special inspections are complete. 66 bridges targeted for additional inspections because they had metal ducts and neat grout. Districts chose to do a few more. This accounts for 77 bridges that had interior soundings and 68 bridges that had exterior soundings performed. So what were the findings from this? We've had delaminations, cracking, spalls, and efflorescence, something new. And that led us to further investigations. And off on the right over here, show that other tendon. This one, believe it or not, it looks bad, but once it got wire brushed and cleaned up, most of the section was still there. We were able to use the vector corrosion inhibitor plate and continue using it. It has some reduced capacity. We took that into account, but it was better to leave it in place. So they weren't all completely, unsalvageable. Further investigations, any significant findings discovered during the special inspection. We thought the investigations consisted of to follow up the special inspection findings, the areas of delaminated concrete, and of course, again, we did material testing. We took cores of the grout, cores of the concrete, looking for chloride and sulfates, and all we found was chlorides. No surprise. Non-destructive testing allows visual surface findings to be investigated without removing concrete. And I want to tell you that we tried a whole bunch of different NDT, but in the end, we kind of moved on with excavations because it was just faster, and we're covering a lot of ground. So visual inspections of soundings, believe it or not, are NDT. We tried ground penetrating radar, which you saw, which we used effectively. We tried impact echo, which gives better results, but it was too slow and hard to schedule, and we just kept on moving. Air-launched GPR was the one you saw. Of course, we did thermal thermography, and we tried main magnetic flux, which is used on external tendons, but had never been tried on external tendons. And it was something that was developed in Germany that FIU, Dr. Adirad Azizi Amini has been working on, and he had a prototype, but it weighed 200 pounds. So if you have the deck, if you're on a snooper, and you want to basically, go under the bridge and measure it, you had to hold up this 200-pound device over your head. It was impractical. Did it work? Yes. They got to come up with a more user-friendly model. But it's actually the technology is heading in the right direction, which is a good thing. Okay, findings. Longitudinal, this is where we found some of the more interesting things. Longitudinal PT. We had PT corrosion, missing grout, strand, and wire breakage. Transverse PT, lack of PT stress, missing grout, duct corrosion, and concrete deterioration, even missing tendons in some locations. Not all deterioration extends into the post-tensioning steel. That was good. To date, no other findings of significance like Roosevelt Bridge have been found. And we're not going to have to do any monitoring because there's nothing that bad out there, and I'll explain why. So District 4, in order to try to get a handle on this thing and try to move us forward as fast as possible, they decided to prioritize their excavations. Where they found in the investigations, they found deficiencies like slack tendons. That was a first priority. It was 9 bridges that had that. Where they had, for priority 2, they targeted bridges with minor deficiencies such as efflorescence and pourbacks, 5 bridges like that. And in their infinite wisdom, and we let them do whatever they want out there, they want to look at 22 other bridges, spot check to see if, they really if it's really kind of working, that there's no issues out there. And that's still ongoing. Should be done this December. So if you take a look at the pourbacks over here, and you took a look at the left, we're calling that efflorescence. It doesn't look like efflorescence, but if you stop to think about it, this is covered with mastic. You got cracks in the mastic. The leachate is coming out of those cracks. It's flowing down the outside of the pourback, and there's obviously an issue. So we removed the concrete, and on the right, this is what we saw. We saw some rusting, and you can see the strands sticking through. You can even see the wedges if you look close enough. It doesn't look good, but there's no loss of section. So what are we going to do? We're going to wire brush this up, put the vector corrosion inhibitor paint on it, and we're going to put a high-quality concrete. We're going to put the mastic on, and we're going to go home on this issue. We had the top slab PT tendons. These are some slack tendons. There's no grout out there either. It's like, this is not good. The good news is that basically this was the top slab. These were all found on the top slab PT tendons, where I said, you have about 2.5 times more than you need. Of course, we validated by a load rating, but it does not affect the capacity of the bridge. So what do? You grout this up, you close it up, and you just thank the fact that you're more lucky than good, and you move on. This was something that kind of threw us. Concrete spalling and tendon corrosion at the fascia of the closure pore. Now, we started chipping this out, and what did we find? We found tendons that had no grout, tendons where the anchorages were missing, some tendon locations where there was no tendons. And we're looking at this and say, what the heck's going on here? And then we noticed that there was no cracking in the roadway on the inside of the barrier wall, on the top of the bottom. So somehow that stress is being transferred. So there's a guy that works for me, his name is Tom Beidelman. He's our state bridge evaluation engineer, runs the permit program. He's a very good modeler. And I said, explain to Tom what I thought was going on. I said, I think we're getting transfer of stresses to the longitudinal tendons through the mild reinforcement of the closure pore, and it's going to the segments. I don't buy into that. I said, well, I want you to prove me wrong because this is your next assignment. And he tried his best to prove me wrong, and what he did was he took a look at various different locations. This is part of his finite element modeling. He looked at 11 to 1,200 different cases of moving loads around, different closure pore widths, different overhang lengths, different distances between webs, and in the end, he found a 3% increase. 3% is nothing. We're not going to worry about that, right? But he didn't believe it. He's diligent. He's trying to prove me wrong. He wants to make me look like an idiot, but that's what I wanted him to do. Go for it, And he did this, took a look at some historical studies dating back 20 years. There were 2 reports out there that found the same results. So what are we going to do? We're going to go back over here, and we're going to, grout those tendons to try to protect the roadway because they don't crush. We're going to, and that will be vacuum grouting. We're going to clean up the steel. We're going to wire brush it. We're going to use the vector corrosion paint, and we're going to do a nice, patching with good concrete on the fascia. And we're going to monitor. This is another instance where it's better to be lucky than good. So, sometimes we get lucky, and we got lucky on these issues. Details were developed and implemented on Roosevelt Bridge have been retained as a benchmark to address similar conditions discovered during special inspections for further investigations, as is what we discovered on these other bridges, which we just looked at. Repairs are determined by deficiencies discovered, patching of excavated concrete to address delamination, vacuum grouting, passivate PT corrosion, replace damage or supplemental PT. We didn't have to do that with any bridge but Roosevelt. Analyze bridge to determine if any repairs need to be made to correct the deficiency, and I just described what we did there. So, and install a monitoring system, which we believe acoustic and strain works the best, but we haven't had to do that in these other bridges. And even though we're not done, we know we're not going to have to do it. We didn't know this was going on, so what are we going to do? We're going to change what we do in inspection, right? We're writing this into the inspection procedures. And what are we going to do? We're going to inspect the top and the bottom of the closure pores for cracking. And then we're going to sound the bottom of the closure pores for delamination. And if the webs have internal tendons, we're going to do the same thing with them. And when delaminations are in the vicinity of the PT, we're going to remove the deteriorated concrete to the top of the PT if necessary. And if deterioration does not extend to the PT, we're going to restore the concrete. If the duct or PT corrosion is observed, we're going to document the conditions and pry the strands to identify movement. If you have movement, you know you've lost some PT stress. Okay? And we're going to test the concrete for the presence of chlorides and sulfates. And if they get to this point, we expect the districts to contact two groups, the State Materials Office and us, because we want to be part of this whole guidance issue so that everything's handled appropriately. Because it takes us 2 years to procedure updated because of all the legal reviews we have to go through now, which is kind of ridiculous in a way, we published a memorandum immediately to make sure that everybody's doing this on future PT bridge inspections. Further investigations are needed that we're going to follow the game plan developed herein. People are saying, are we having the same problem on our newer bridges? And we're not having the same problem on the newer bridges because we have had, this is our 3rd round of problems with segmental bridges. The first one was the late 90s, the other one was the early 2000s, and then this is the last one. Well, what we've done over the years, design has improved the PT protection systems on newer bridges starting in 2001 and continuing. Improved specifications, improved details, improved construction procedures, ducts, that's where the plastic ducts that can be pressurized come in, and improved grout. We moved away from neat grout, we went to thixotropic grout. And we've recently gone to replaceable tendons with flexible filler, which is a wax type material. And, but you can't use that everywhere. So we are still going to have more grouted tendons than replaceable tendons with flexible filler, and the reason for that is on the top slab you don't want a duct with a flexible filler in it because it's not going to support wheel loads and could cause some problems with the deck. But anywhere we can, we're going to use flexible filler, and this is what they're doing in France. I don't know how he swung it, but the state structures design engineer and one of his assistants got a nice trip to France to go see what they do in France, because this technology was developed in France. So they never sent me to France or any other place outside the country. Construction also improved construction practices and operations implemented on newer bridges. This is the most important thing, training for contractors and inspectors. And that was on PT stressing, PT grouting, and flexible filler operations, right? And the reason for that's so important is this. If your contractor doesn't know what he's doing, and they didn't know what they were doing when they built some of these earlier bridges, you have 0 chance of getting an error-free bridge. You're going to have problems. And the thing is, if your CEI isn't trained, he's not going to know if the contractor is missing something. So to me, this is the best thing that they did. The Materials Office also came up with new material acceptance procedures, and there's been a lot of changes in construction that occurred when I was in that office, just about this time. Improved planning, and quality control and quality assurance for construction operations. When I say improved planning, goes beyond segmental bridges. You sit down with your contractor, you got a major operation coming up, what can go wrong and what's your workaround? Like for something like this, what happens if you lose your pump? You know what I mean? Make sure that you have a plan, try to think of everything, and the contractors love it. They actually absolutely love it because we're helping them do a good job and we're getting better product for it. I'm behooved to put this in on every DOT presentation presenting FDOT information because our new slogan is the vital few: safety, mobility, and innovation, right? And that's what we have. The last one is hiring and retention. Well, we try to entertain our staff as much as we can, but at the bottom line, I'll say this very quietly, pay them a little more money, that would help too. That's it. Are there any questions? You know?
No, just I was curious if you guys found any standing water inside the boxes.
Yes, and that's the reason that they left them open. I kind of glossed through that, and they were sitting in the tendons, and they had salt in them and stuff like that. So the idea is, and of course, everybody wants to move forward. And the materials office insisted until we know where the water is coming from, it has to. We can't deal with this. So that was where we went with that. You know, the Kevlar and the methacrylate and the injection grouting and the double, the 2 layers of epoxy to stop it. It has stopped it. And when it dried up, that's when we closed them up and made the repairs. As this is my last presentation, oh, I don't have it over here. I have a slide anyway, but whatever. I want to thank you very much. I'm retiring at the end of the month. This is a great group. I was there at the very beginning when this started in Orlando, and it's grown a lot. Every year it gets better and better. The working groups, I think, are the real engine of what's going on now. If I do retire, I'm going to miss this group, but I think that I'm very proud to have been part of this for all these years. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.